imagine you are writing a check for $100.
Okay, a physical paper check.
Yeah, a physical check. You write the number 1, followed by 2 zeros, you sign your name, and you hand it over.
Right.
But imagine the person you handed it to takes a pen and just adds a single vertical line through your number 1 to make it a 4.
Oh, wow. That's, yeah.
And suddenly, you're on the hook for $400 instead of $100. When we rely on really simple symbols to represent immense value, we kind of open the door to human opportunism.
We really do. I mean, for centuries, merchants and bankers have fought this exact kind of fraud.
Exactly. And today, we're going to look at how a modern computer programmer builds digital defenses against that very ancient, very human problem. Welcome into the deep dive.
It's great to be here.
We have a really fascinating mission for you today. We are looking at a highly specific snippet of programming logic from a blog post. It's titled Notes on Haskell-Programming.
Part 190.
Right, part 190. This was written by a developer named Ang and published on July 18, 2026.
It's honestly a remarkable piece of source material. I mean, we spend so much time thinking of computer code as this pristine, frictionless environment of, ones and zeros.
Totally divorced from the real world.
Exactly. But what Ang's blog post captures is the messy reality. Code is ultimately a bridge to human behavior. It has to accommodate our history, our languages, and, well, in this case, our tendency to tamper with financial documents.
That is the perfect setup for the core puzzle Ang is tackling here. So the goal of this code is to take a standard Gregorian year, specifically the year 2026, and translate its digits into Chinese numeral text.
Right.
But the code cannot just provide one standard translation. It's required to support 2 completely different types of Chinese writing simultaneously, depending on the context. Okay, let's unpack this.
Please do.
We're taking 4 simple digits, 2026, and building a software architecture to navigate this whole linguistic maze.
Which means before we even look at a single line of the Haskell programming language, we really have to understand the linguistic data itself.
Yeah, that makes sense.
You can't build a container until you know the exact shape of the water you are trying to hold. So Ang's code is working with regular, everyday simplified Chinese, and then a secondary set labeled explicitly in the notes as formal, financial.
Right, and I have to admit, when I first read that, I was genuinely confused. Wait, why do we even need a separate financial version of a number?
It's a fair question.
Because if you look at the everyday Chinese character for the number 1, it's just literally single horizontal stroke. It's elegant, it's perfectly clear. I initially thought, maybe this was like a dialect issue or regional difference between, say, mainland China and Taiwan. But it's not geographical at all, is it?
Not at all. No, it is entirely about security.
Security.
Yeah. Think back to your opening scenario with the check. If the character for the number 1 is a single horizontal stroke, think about how easily a bad actor could alter a physical contract.
Oh, I see where you're going with this.
Right. You take a brush or a pen, you add 1 vertical stroke through that horizontal line, and you have instantly transformed the number 1 into the character for the number 10.
Wow.
And if you add a couple more strokes, it becomes 1,000.
Oh, wow. So the simplicity of the everyday numeral is actually like a massive security flaw in finance.
Precisely. To combat this, historical banking systems developed formal versions of these characters. They are deliberately complex, dense with multiple strokes, making them incredibly difficult to alter without the forgery being, immediately obvious to the naked eye.
That is brilliant.
So a programmer like Ang, building a system that might interact with financial applications, can't just rely on the simple everyday numbers. The software must be capable of rendering the tamper-proof formal ones upon request.
Let's look at the actual mapping Ang provides in the source to really illustrate this. We'll run through the 0 through 9 dictionary because the contrast is really striking.
It is.
Let's start with 0. The Arabic digit 0 maps to U in regular Chinese. And in the formal financial column, it maps to, well, exactly the same character.
Right, it doesn't change at all.
Yeah. But then 1 maps to for regular and 2 for formal. 2 is U and 3. 3 is U. And 4 goes from India to U.
The stroke count just explodes on those formal ones.
It really does. 5 is U and U. 6 is E real 2. 7 maps to 2, and E is U and E3. And finally, 9 is E and U.
Yeah, if you look at the everyday characters for 1, 2, and 3, they are literally just one horizontal line, two horizontal lines, and three horizontal lines. But those formal counterparts, they are sprawling characters with 10 or more strokes each. They look like entirely different words.
They really do. And going back to 0 for a second, I noticed that anomaly immediately. Why is 0 exactly the same in both columns?
Because the everyday character for 0 is already complex enough. I mean, it requires 13 distinct strokes just to write it.
Oh, so no one is forging that.
Exactly. No one is easily forging that into another number, so history just didn't bother inventing a secondary, more complicated version. The everyday version was already secure by default.
That is fascinating.
Ah.
But man, it presents a real headache for the programmer.
Oh, absolutely.
Because you have some numbers where the regular and formal characters are radically different,
Yeah.
and some where they are totally identical. So how does Aang deal with this?
My initial instinct, if I were hacking this together, would be to just build two completely separate reference lists.
Like two different dictionaries.
Yeah. I'd make one dictionary for regular numbers and a completely different dictionary for the financial numbers.
That is a very common approach, especially for beginners, but it introduces significant fragility into your software.
Well, if you maintain two separate lists, you have two separate sources of truth. If you ever need to update a character or fix a bug, you have to remember to do it in multiple places. What's fascinating here is how Aang takes these two diverging linguistic paths and unifies them into a single master reference table, which is named Digit Chinese Map in the code.
Unifying them sounds great in theory, but how do you actually structure that data? We need a container that can hold the Arabic digit, the regular character, and the formal character all at once in a way the computer understands.
Right, and this is where we introduce the concept of a tuple. In Aang's Haskell code, Digit Chinese Map is structured as a list of 3-element tuples. The data type is defined as char, char, char.
I was trying to visualize this tuple concept earlier, and the best analogy I could come up with is like a fixed bento box.
Oh, I like that.
Right. Imagine Aang is constructing a customized 3-compartment bento box for every single digit from 0 to 9. Compartment 1 holds the Arabic digit. Compartment 2 holds the everyday Chinese character. And compartment 3 holds the complex financial character. They are permanently packaged together.
I think the bento box analogy works really well because it emphasizes the structural rigidity. A tuple is not just a loose bag of items. It is a fixed, ordered sequence.
Right. So if I ask the program for the data on the number 5, I don't just get the character pho. I am handed the entire fixed bento box. I get the Arabic 5 in slot 1, the regular win in slot 2, and the formal in slot 3. They travel through the code as a single unit.
Exactly. And to understand why this structure is so powerful, we should really look at the code diff, the snapshot of the old code that Aang is replacing.
Yeah, the blog post actually shows us the previous, simpler method.
It does. Aang was using a built-in function called zip. The old code looked like this. Zip 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then
So it just takes a string of Arabic digits and literally zippers it together with a string of regular Chinese characters.
Exactly. It pairs the first item of string A with the first item of string B, which works perfectly fine if your world only has 2 dimensions. But the moment the requirement for financial characters was introduced, that zipper model completely broke down.
Because there's no third track on a zipper.
Exactly. If you just add a second zip command somewhere else in the code base for the financial characters, you create the exact problem we discussed earlier, fragmented truth.
You'd essentially have 2 different assembly lines trying to zipper things together independently. If one gets out of sync, your entire program is printing the wrong translations.
Precisely. By transitioning to the list of 3-element tuples your bento boxes, Aang centralizes the truth. There is now only one place in the entire code base where the translation rules live. It makes the architecture incredibly robust.
Okay, so our data is beautifully organized. We have our stack of 3-compartment bento boxes, but this introduces a new, highly practical problem.
What's that?
Well, the translation functions that are going to process our year 2026, they don't want the whole bento box. If I am generating a financial report, I only want the Arabic digit to match against and the formal character. I want compartment 1 and compartment 3. I have 0 use for compartment 2. So how do we open the box, extract only what we need, and leave the rest behind?
We need a filtering mechanism. And this brings us to the core technical operation of this deep dive. Aang solves this data extraction problem using a feature of Haskell known as a list comprehension.
Now, I want to be careful here because reading raw programming syntax out loud is usually a terrible experience for the listener.
Oh, it really
Yeah,
is.
if you look at Aang's blog post, the list comprehension is full of brackets, commas, and arrows. It looks like a math equation exploded.
But Aang takes the time to explain the underlying logic of the syntax, and I think that is what we should focus on.
The logic is actually quite elegant. A list comprehension is essentially a way of generating a new, highly specific list by filtering an existing broader list. Aang notes that the most crucial piece of syntax in this operation is the vertical pipe symbol. It's just a straight up and down line, usually located above the Enter key on your keyboard. In Haskell, that pipe symbol acts as a massive logical hinge. Aang explains that you read it out loud as the word where or the phrase such that.
Think of it like setting the conditions for entry into an exclusive club. You are telling the compiler, build me a brand new list of items such that the items meet these specific criteria.
Okay, let's apply that logic to Aang's actual code. To extract just the regular Chinese translation, Aang writes a comprehension that basically translates to this. Give me a new two-part tuple containing only the digit and the regular character, where the data is pulled from our master bento box lists.
Notice what is happening there. We are fundamentally changing the shape of the data. We are pulling a 3-element tuple from the source, but we are constructing a 2-element tuple as the output.
Here's where it gets really interesting. How does the program know to just ignore that third piece of data? I mean, if the bento box has 3 compartments, you can't just pretend the third one doesn't exist. The compiler will throw an error if the shapes don't match.
Right. It demands structural integrity. You have to acknowledge the third compartment even if you don't want its contents.
To solve this, Aang uses an underscore symbol in the code. In the filter for the regular translation, the underscore sits in the third position. In the filter for the formal translation, the underscore sits in the middle position.
The underscore operates as a wildcard. It is a way for the programmer to explicitly say to the compiler, I am fully aware there is a piece of data occupying this slot, but I do not care what it is, and I do not want to use it. Discard it.
It is so brilliant. Going back to our bento box analogy, the underscore is like telling the kitchen, I am ordering the number 5 box. I want the digit in compartment 1, and I want the formal character in compartment 3. I know there's regular rice in compartment 2, but just dump it in the trash before you hand me the box.
What makes this so powerful in Haskell is its visual readability. In many other programming languages, you would have to write out clumsy indexing code to achieve this. You would have to write manual instructions saying, access array item 0, then skip array item 1, then access array item 2.
Which is tedious to write and really annoying to read.
Very. By using pattern matching with the underscore, the code visually mimics the shape of the data it is extracting. Any programmer looking at Aang's source code can instantly see the exact structure of the tuple and immediately recognize which pieces are being kept and which are being thrown away. It is self-documenting code.
Okay, so the foundation is fully laid. Our master table holds all the linguistic truths. Our list comprehensions are acting as the perfect bouncers, ensuring only the correct translations make it through the door. Now we have to look at execution. We have the year 2026. How do we actually run it through this architecture to get our final Chinese text on the screen?
Aang builds 2 distinct top-level functions to handle the final execution. The first is named year to Chinese, which handles the everyday numeral output. The second is year to Chinese formal, which triggers the tamper-proof financial output.
So if I feed the number 2026 into the first function, it spits out. If I feed it into the formal function, I get yours. I see the results, but I want to talk about the mechanics happening inside those functions. How are they processing the year? Because they don't just magically swallow a 4-digit number and spit out characters.
No, they rely on a sequence of 3 specific operations: show, map, and pack. It is a pipeline.
Let's trace our year, 2026, through that pipeline. The first step is the show function. From what I understand, when you pass the integer 2026 into the program, the computer sees it as one single mathematical monolith. It sees the mathematical concept of 2026. It doesn't see 4 distinct characters.
That is a crucial distinction. You cannot translate a math concept using a character dictionary. You have to break it apart. The show function in Haskell takes that integer and converts it into a string format. It shatters the monolith into a sequence of individual characters, a 2-2, a noun, and a 6-3.
Okay, so now we have our raw materials. The next step in Aang's pipeline is the map function. I like to picture map as a relentless high-speed assembly line.
An assembly line is an excellent way to conceptualize it. Map takes a specific instruction, in this case, our translation lookup tool, and applies it systematically to every single item moving down the belt.
So our string of characters hits the bolt. First up is the tufend. The map function grabs the tufut, runs over to our tuple dictionary, uses the list comprehension to filter out the bento box, grabs the Chinese character and puts it back on the belt. Then it grabs the Dewik and does the exact same thing. Then the next two, then the six. It doesn't care how long the string is, it just relentlessly applies the translation rule to every single piece.
Exactly. And once the map function has finished its work, you are left with a sequence of translated Chinese characters. But they are still loose items. They aren't a cohesive piece of text yet.
Which brings us to the final step, the pack function.
Pack is the shipping department at the end of your assembly line. It takes that loose sequence of translated characters, compresses them together efficiently in the computer's memory, and seals them into a unified text object that can be safely printed to a screen or saved into a database.
So what does this all mean? We have followed this incredibly logical journey. We built a robust, centralized tuple architecture. We utilized an elegant list comprehension with wildcard underscores to filter the data. We sent it through the show, map, and pack assembly line. It is a fantastic piece of engineering. But then I look at Eng's notes at the end of the blog post, and I have to push back on something.
Oh, what stands out to you?
Eng builds two completely separate functions to execute this year to Chinese and year to Chinese formal. But right there in the text, Eng explicitly admits, even though having one function should be adequate, more refactoring in future, Eng is literally telling the reader that writing two functions is redundant and that one dynamic function would be better. If Eng knows it's not the optimal way to write it, why publish it like this? Is it just laziness?
I wouldn't call it laziness at all. In fact, it is a remarkably transparent look at a concept we call technical debt. Or more accurately in this scenario, the pragmatic reality of prototyping.
Prototyping, meaning like just getting it to work before making it pretty.
Exactly. Look at the title of the source material. This is Notes-on-Haskell-Programming, Part 190. This isn't a press release for a polished version 1.0 commercial software product. It is a snapshot of a developer's ongoing learning process. It is the messy middle of creation.
I suppose when you are deep in the weeds of complex tuple structures and list comprehensions, just getting the code to compile without crashing is a victory in itself.
It is a huge victory. When programmers tackle a new problem, they often build the verbose, explicitly separated version first. Writing two distinct functions is easier to test. If the formal translation breaks, you know exactly which function to investigate. It lowers the cognitive load while you are proving that your underlying logic, the tuple map and the filtering, actually works.
You build the scaffolding to prove the building won't collapse, and then you worry about the interior design later.
That is a great way to frame it. Eng leaves a note, more refactoring in future, which is essentially a promise to come back later, tear down the scaffolding, and merge those two functions into one highly dynamic, elegant piece of code. It is an honest acknowledgement that software development is an iterative process. You rarely jump straight to perfection on the first try, not even by part 190 of your journey.
I really appreciate that human element. It strips away a lot of the intimidation surrounding programming.
Right.
It reminds you that behind every impenetrable wall of syntax, there is just a person leaving little sticky notes for themselves to clean up their mess later.
It grounds the entire discipline. Code is written by humans for humans.
Let's recap the journey we took you on today. We started with a very real historical human problem. The ease with which simple ink strokes can be forged on a financial document, necessitating a complex, formal Chinese numeral system.
Right.
To handle that linguistic dual reality, we watched a programmer construct a unified three-compartment tuple bento box to store the Arabic digit alongside both Chinese variations safely.
Safely and systematically.
We explored how to extract that data using the elegant filtering logic of Haskell's list comprehension, wielding the wildcard underscore like a bouncer at a club. We traced the year 2026 through the show, map, and pack assembly line. And finally, we discovered that even beautifully architected code is often just a rough draft waiting for a future refactor.
As you process all of this, I want to leave you with one final thought to explore on your own. We spent this deep dive marveling at the technical elegance of Haskell. We admired the tuple structures and the list comprehensions, but consider the root cause of all this engineering.
The human element.
Exactly. The only reason Eng had to build this elaborate data architecture is because human beings are prone to altering horizontal lines on financial contracts. It forces us to ask a broader question. As we look around at the vast digital infrastructure running our modern world, how much of our most sophisticated, complex computer code is actually just an elaborate scaffolding built to manage the paranoia, the fraud, and the messy imperfections of human nature? Are we engineering brilliant math, or are we just writing digital laws to govern human flaws?
Wow, that completely flips the perspective. The code isn't just solving a math problem, it is policing our behavior. Thank you for joining us on this exploration of Ang's work. Keep questioning the systems you interact with. Look for the human history hidden inside the logic, and keep finding the magic in the code around you. Until next time.